Alright, I want to take a minute and look at this equation with you, the inverse square law of light, or the flux versus distance equation here, and do a couple example problems. So first though, I just want to connect this to the idea of brightness, because we have sort of our intuitive sense of what brightness means, and it doesn't really jive with this equation. So let's think about that real quick a second. This F represents flux. And the way to understand that is that's the brightness that your eye sees, right? That's how bright you perceive an object to be. That would be the flux. Technically, it's the amount of light passing through like a square meter of area. But we can think of that as the light passing into our eye or the light passing through a telescope. Now this E, which we refer to energy, is really the brightness that the object really is. It's how much energy is leaving that object. And as you can imagine, the brightness that we perceive, this flux, right, depends on how far away we are from an object. You know, there's a certain amount of energy that's being given off by a light bulb. That would be E. That doesn't change with how far away you are. But as you get further and further away from that object, it's going to look fainter and fainter. And that's that flux that we're perceiving. So the word brightness is really kind of misleading. Because we're talking about two different kinds of things. And later on we'll see that we give these things sort of technical terms like intensity and luminosity so that we're clear about which of these things we're referring to, the intrinsic brightness or the perceived brightness. But let's not worry about that quite yet. Let's just do a couple example problems. For this particular equation, I'm going to focus only on ratio problems. Like if something's changing by a factor of 2 or a factor of 4, how does something else change? So we're not actually going to worry about plugging in values of watts and meters and all that stuff. We're just going to be thinking about how things are changing. So let's just do one quick example problem. Let's say that I've got two objects, two stars or light bulbs or whatever you want them to be, and they're both the exact same brightness. Like they have the same amount of energy going out. Their intrinsic brightness is the same. So in other words, E is equal for both of these two things, right? And let's just say though that I have two observers. One observer is nice and close, and let's say that the other observer is way down here. And I'm not sure the drawing's to scale, but we'll just say that this observer is 4 times further away. 4 times further away. So the question is, how would the perceived brightness of this object be different for this observer? In other words, how much fainter would the object be for this observer than for this observer? So like all ratio problems, we look at this equation and we can sort of rewrite it by asking ourselves, well, what's changing? In a ratio problem, if something doesn't change, we replace it with a 1. Alright, so I'm comparing these two situations on both sides. So if something's not changing between the two situations, then we leave it as a 1. So in this case, the flux is something that we perceive to be changing, right? It's the perceived brightness of this object, so that's what we're trying to figure out is what that flux is going to be. The energy of these two objects is the same, right? So that means the E, we're just going to replace it with a 1, right? Because in a ratio problem, it's not changing, we use a 1. 4 pi, that's a constant, and so it doesn't change, and so we'll replace that with a 1 as well. So there's a 1 there. It won't really matter at all, in fact, because we're just multiplying 1 times this distance squared. And so the distance is changing, right? And instead of putting in the distance, we don't actually know what the distance is, but we know that it's 4 times bigger. So we're going to replace the d with a 4. And again, the most important thing about these ratio problems is that we remember to keep the exponent, right? So we still have this squared here. So what this tells us is that the flux will be 1 over 4 squared is 16, and we multiply by 1, it doesn't change. So 1 over 16. So we ask ourselves here, let's see, it's 4 times further away. It must be fainter. And so in fact, we can see that it's a 16th what it originally was. So you could say this a couple different ways. You could say that the flux equals, 1/16th its original. You could say it something like that. Or you could say, well, I know it's fainter, so I'm just going to say the flux is 16 times fainter. It's another legitimate way to say it. Alright, so there's one type of ratio problem that we could try to do with this equation. Let's take a look at another example. Let's say this is a case where we are looking at two objects, and we happen to know that one of the objects is twice as far away as the other. Right, so here's one object right here, and the other object's twice as far away. All right, now as we look at these two objects, they appear to be the same brightness in the sky. They look the same. Okay, so we would say their apparent brightness that translates to the flux, right? So we'd say the flux is constant between these two objects. Right? So naturally then the question I'm going to ask you is how much brighter intrinsically is one of these two objects, right? How does the energy coming out of one of these objects compare? Like how many times bigger, right? So this one is a case where the distance is 2 times bigger. All right, so let's check this out. So let's just call this, just because this might get confusing, we'll call this object A and this object B, just so we know what we're referring to. So let's set up this ratio problem. Right? If the flux is constant, then we start by saying, okay, we're going to replace the F with 1. And that's going to equal the energy. Now that's what we're expecting to change. So we'll just leave an E there. Over 4 pi again is a constant, so we'll just leave that out or replace it with a 1. Times distance squared. Well, the distance here is 2 times bigger in case B, so we'll put a 2 here and we'll say squared. So I'm going to change this equation now. To simplify it here, it'll be 1 equals just E over 4. And we want to solve for this energy, right? So I'm going to multiply both sides by 4, and they'll end up here with that E equals 4. Now, what does that mean? Well, let's think about this. This object appears to be the same brightness as this object. But this one's way further away. B is way further away. So B must intrinsically be much brighter, right? This guy must be brighter. It must have more energy that it's giving off because we're seeing it to be the same brightness even though it's so far away. And so what we just did was we turned this quantitative, right? And we said, well, how much brighter is it? And so what we found out here, the way we would write this, we'd say is that B is 4 times, well, I should be careful, right? The word bright is very misleading. So I'm going to say B has 4 times more energy, or it's giving off 4 times more energy. Okay, so there we solved it for a different variable in this case. But it's helpful when you do ratio problems to sort of stop and reason a second and say, what did I actually figure out? You know, what did I actually solve? And make sure it's consistent with our conceptual understanding of the equation.